Good afternoon, everybody. Can you hear me?
Yes, ma'am.
Yes,
Yes,
ma'am.
I'll be talking less. My throat is gone completely. Uh, These things I could not have discussed with you in an official forum. That's why I just put the message. Okay, let's start off with Gauss law and conductors. So till now, whatever we discussed, Gauss law, just to remind you about what is Gauss law. Till now, we have seen that flux is equal to charge enclosed by epsilon naught. And we use this to find out electric field. And we found it's very easy to find out electric field whenever there is a geometric symmetry of the field and the charge distribution. Now, let us move to conductors. Here, see, remember, your Coulomb's law could be used only for insulators or for charges that don't move. But Gauss law can be applied to charges that to conductors. So let's take a conductor. So if you remember, I have told you conductor is something where charges can move. Okay, so if I take a conductor and dump charges on it and leave it on the floor, the charge would just flow off. Because it's moving, it will just leave the body. Okay, so if you want a conductor to remain charged, what should you do? You should see that it is insulated from any other conductor around it. Are you getting the point?
Yes.
Yes.
Okay, so the conductor, if you're charging it, you should see that it is insulated from any other conductor around it. So that's what is shown in this picture here. There is a thread from which you are hanging your conductor, and then you are dumping it with some charge Q. Okay, so what happens in the case of a metal or a conductor is that charges can move. So all these, the rest of the material is neutral. The rest of the material is neutral. There are positive charges, there are negative charges, but it's neutral. But this excess charge that you have put, they quickly, let us say they are negative charges. They start feeling a repulsive force from each other and they want to move as far away from each other as possible. They want to move far away from each other as possible. So how far can they go? They can go till they reach the surface of the material. They can move away till they reach the surface of the material. Okay, for no other configuration, if they stay anywhere inside the material, they are not really far away from each other. So, to attain that state of repulsion and the maximum stay away from each other, because you know that like charges want to stay away from each other, so the potential energy of the system is a minimum, and that is equilibrium. So here also, they go quickly occupy the, even if it is positive charge, same thing, they will go and occupy the external surface of the conductor. And this will happen in a very, very short time of around nanosecond. Okay, and this process is called attaining electrostatic equilibrium. This process is called attaining electrostatic equilibrium state. And once they have gone and sat there, they will not move. They will not move. That is why it's called electrostatic, no movement. And what is the consequence of this? Let us see. If I want to find the electric field somewhere inside this body, I can simply draw one Gaussian surface and try to find out what is the charge enclosed by this Gaussian surface. If this is my Gaussian surface, I can draw the Gaussian surface and try to find out what is the electric field somewhere inside. Or let's say I want to find out the Gaussian field at a point here. Then what you will get is that there is no charge inside the Gaussian surface, because all the charge went and sat on the surface. What is inside is only neutral, equal number of positive and negative charges of the atoms. Therefore, Q will be equal to 0. And you know that when Q equal to 0, that means flux is going to be equal to 0. And that would imply that electric field is going to be equal to 0. Okay, so you can conclude that electric field is equal to 0 inside an isolated charge conductor which is in electrostatic equilibrium. Please remember this. This happens only after electrostatic equilibrium is achieved. They go and sit on the surface. Once you are sitting on the surface, there is no charge inside. Therefore, at any point, you take smaller and smaller Gaussian surfaces and see at every point of these Gaussian surfaces, electric field will be zero because charge enclosed is zero. Okay, so that is one of the outcomes of electrostatic equilibrium. Next thing is, as I told you, since charge is zero, charge density is also zero. Because after all, charge density is charge divided by volume. Therefore, charge density is zero inside the conductor when it is in electrostatic equilibrium. And please remember, I have discussed all this for an isolated charge conductor. Isolated means it is not in touch with any other conductor. Okay. Now the question is, did you understand this, what I discussed?
Yes, ma'am.
Okay. Okay. Now the next question is, okay, I have a conductor like this. I put a charge Q. It went and sat on the surface. Fine. Fine. What if this conductor has a cavity? What if there is a cavity? What if there is a cavity? Then there are two surfaces, one inner surface and one outer surface. In this case also, will all the charge go and sit at the outer surface? Will be the next question. Yes. Now also, all the charge will go and sit on the outer surface only. Okay. And here, the charge will be zero. On the inner surface, the charge will be zero. Why? That is because by going and sitting on the surface, it is still able to keep the electric field zero everywhere inside. It is able to keep the electric field zero everywhere inside. Charge enclosed by the Gaussian surface is zero. Therefore, electric field is zero inside. So that is achieved if all the Q goes and sits at the surface. Now I am coming to third situation. What if I have my conductor like this? I put a charge Q. I have a cavity, and inside the cavity, I have a charge Q prime. Please listen again. I have a conductor. Inside that there is a cavity, and inside the cavity there is a point charge Q prime. And let outside have no charge. Let outside have no charge. That is, this body of this conductor is not going to have any charge, but inside the cavity there is a Q prime. Now how equilibrium will be reached? Let us see. What is the condition for equilibrium? Anyone?
Isolated.
Electric field should be, charge should not move. Electric field should be zero in the body of the conductor. So which is the body of the conductor? The body of the conductor is this one. This is the body of the conductor, right? This entire thing is the body of the conductor. Electric field has to become zero. How will it become zero? This will become zero if there is a charge minus Q prime. Am I telling the right thing? Yeah, I'm sorry. Sorry. So this is my conductor. This is my cavity. There is a point charge Q prime. Now, everywhere here, the electric field has to be zero. That is called electrostatic equilibrium. How will that happen? Tell me. That will happen if, please remember, this is a conductor. Because it's a conductor, it is having already equal number of electrons and protons. And electrons can move, you know that also. Okay. So let us say Q prime is a charge inside the cavity. So what will happen is some negative charges will move from the neutral metal. Okay. And this negative charge that is going to go and settle on the inner surface will be minus Q prime. A charge minus Q prime will go and sit on the inner surface. If minus Q prime goes and sits on the inner surface, automatically plus Q prime will go and sit on the outer surface. Okay? The body of the conductor is neutral, but it has got charges. Okay? So to make the inside of this body E equal to 0, some electrons from the metal will flow and sit on the inner surface. How much charge will sit? Minus Q prime will go and sit. And if minus Q prime goes and sits on the inner surface, plus Q prime will be sitting on the outer surface. So now you use your Gauss law and see. I'm going to draw one Gaussian surface here. What is the net charge enclosed by the Gaussian surface? What is the net charge enclosed by the Gaussian surface?
Plus Q. 0.
0. Net charge enclosed by the Gaussian surface is 0. Therefore, electric field is 0. So this is the way electrostatic equilibrium will be established. Okay, and now this kind of charges, there was first no charge on that body at all, but then the charges got separated. Some negative charge went and sat on surface, equal positive charge went on sat on the other surface. So these kind of charges which are going and sitting like this are called induced charges. What are they called? They are called induced charges. So induced charges get created so that electric field continues to be 0 and you are able to get electrostatic equilibrium. Okay. Now to test whether you understood what I'm saying, I will just add a page here and give you an exercise. Okay. I have a metal. I have a cavity. Inside the cavity, I have a charge plus 2 nanocoulomb. So now how will electrostatic equilibrium be achieved? Let me call this surface as A. I'll call this surface as B. On surface A, what will happen?
We will have minus 2 nanocoulomb.
Right. So what will happen is from the body of this conductor, minus 2 nanocoulomb will come and sit on the surface A. So as a result, what is happening? There is a deficiency of negative charge on the other side. So therefore what will happen? You will have plus 2 nanocoulomb on the outer surface. Okay. So therefore, you can see that the induced charges are minus 2 nanocoulomb on surface A and plus 2 nanocoulomb on surface B. Okay, now let me check whether you understood by giving you another example. I have a sphere or I have a thick spherical shell I have a thick spherical shell with a charge -4 nanocoulomb, and I am dumping a charge +6 nanocoulomb. Now try to tell me how electrostatic equilibrium will be achieved. What will be the charge on surface A? What will be the charge induced on surface B? On A, what will happen?
+4 nanocoulomb.
+4 nanocoulomb. That you can close your eye and say. Okay. What will be the charge on the outer surface?
+2 nanocoulomb.
Why?
I mean, it should originally have -4 nanocoulomb, but we are adding +6, so the difference would be +2 nanocoulomb.
That's right. You have dumped one +6 nanocoulomb here. So that +6 has not got lost anywhere. It is there on that body. This is an isolated conductor. So that +6 nanocoulomb hasn't gone anywhere. Okay. Out from that +6 only you got this +4. Therefore, what is left is only +2 nanocoulomb. Okay. And by doing this, it's able to ensure that E is 0 inside. Guys, did you understand this? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yeah. So maybe one last thing I just show you this, because I can't talk much. I have I have tried to just solve some problem for you. Look at this. A long hollow cylindrical conductor is surrounded by a coaxial conducting hollow cylinder. So two cylinders are there. There are two cylinders. Okay. There are four surfaces A, B, C, D. Inner conductor has +2 Q charge. Outer cylinder has -3 Q charge. Find the charge that resides on the surfaces of the two conductors. You just go through this later. So you will realize that surface A need not have any charge. Without having any charge itself, electric field will become 0 on the body. So all the excess charge will go and sit on B. So that is +2Q. Now, if you want electric field 0 on the second conductor, so C should have the same charge as B. Therefore, -2Q. Then what is left will go and sit on the outer surface. Is this clear now?
Yes, ma'am.
Okay. Okay, so we have discussed what is happening inside out, right? But what about outside? What about outside? The excess charge is all going and sitting on the outer surface. I mean, though we draw outer surface, it's not really outer surface. It sits in a thin layer. It sits in a thin layer of the material. That's why this author has shown it like this. In a thin layer, it goes and sits. Okay. So now, if there is charge sitting like that, that means electric field outside has to be non-zero. Outside the surface of the isolated charge conductor in electrostatic equilibrium, electric field has to be non-zero outside. Inside it will be 0, but outside it will not be 0. That's one thing. Next thing is, not only it is not 0, the electric field also will be perpendicular to the surface of the conductor at every point. It will be perpendicular to the surface of the conductor at every point. Like for example, if this is my conductor surface, okay, and if I say that positive charges are going and sitting like this, okay, now every point here, the electric field will be perpendicular to the surface, non-zero and perpendicular to the surface. And I'm drawing away from the conductor because it is positive charge. Okay, this is how electric field will be. How do I know that it is perpendicular to the surface? For that, there is an argument. Listen very carefully. For a minute, let us think that the electric field is not perpendicular. Assume electric field is not perpendicular. If electric field is not perpendicular, you can actually draw two components of the electric field. You can draw two components of the electric field. This is the perpendicular component, and this is the parallel component. Did you understand this point?
Yes, ma'am.
If electric field, let's assume it is not perpendicular to the surface, then this vector can have two components, one like this, one like this. Okay. Now, what should this fellow do? What should this fellow do? You know that F is equal to QE. You know F is equal to QE. So, if such a field existed parallel to the surface, what would that field do? It will start exerting force on the charges sitting on the surface and move them. Yes or no?
Yes, ma'am.
Right. What are moving charges called? Current. Moving charge is current. But the absence of any such surface currents, makes you conclude that no such parallel, or we may also call it tangent to the surface, no such tangential component or parallel component exists. So what do you conclude from that? All the electric field has to be perpendicular to the surface. This is the argument. You can just use logic and come to the conclusion that for any charge conductor isolated in electrostatic equilibrium, electric field has to be perpendicular to the surface. Next, what will be the electric field? Let us see. For that, let us draw a pillbox. Pillbox Gaussian surface. Okay. You're finding that electric field is uniform and it is going to only cut through this top cap. There is nothing cutting through the bottom cap because there is no electric field line here. That's the difference between insulator and conductor. In insulator, we drew this kind of a cap and we said a pill cap, and then we said electric field is like this and like this. So through both the caps they are cutting. But here electric field is zero inside, non-zero outside. Therefore, electric field is only going to cut through this. Therefore, flux will be equal to what? E into A. Integral E dot dA becomes E into A, and that will be equal to charge by epsilon naught. Okay, but you know that charge contained within this area A can be written as sigma into A by epsilon naught. Okay, now from this you will come to the conclusion that you just cancel out A and A. You will come to the conclusion that electric field will be sigma by epsilon. What is sigma?
Surface charge distribution.
Do you remember what is the expression we got for an insulator? For insulator, what is the thing we got? Tomorrow is exam. For insulator, we got sigma by 2 epsilon naught. Because there are two caps, EA, EA. So 2 EA equal to Q by epsilon naught. Okay, therefore you got E is equal to sigma by 2 epsilon naught for insulator. Therefore, this is a very important conclusion. The electric field near an isolated charge conductor is twice the field near an insulated charge conductor. Take an isolated charge conductor, electric field just outside is 2 times the electric field outside. A similar geometry insulator. Are these things clear, guys? If you have any doubts, please ask. Finally, to wind up, let us consider an isolated charge plate this time. Till now, when we talked of isolated, when we talked about insulator, a sheet meant just give me some 2 minutes rest. I'll come back. Okay, I'm back. When we discussed insulator, when I said a surface, we never thought about thickness of the surface. We never talked about thickness. It was almost zero thickness. We just considered a single layer. Okay? But when you consider a charged, isolated conductor sheet, you must consider that there are two surfaces. The thickness may be negligible, but there are two surfaces, left surface and right surface. So what happens is, when you dump some charge, the excess charge will go and sit on both the surfaces. The left and right surface, it will go and occupy. Okay? Then you will ask, what about this side? What about the surface? Yes, it will sit. But since the thickness is small, you can neglect it. So now, what happens is, it's a single sheet of metal, but it will behave as if there are two sheets. And within the center, there will be nothing. All the excess charge will go and sit on the two surfaces. So now, when you want to find out what is the electric field at the center, you can treat these two now like insulating sheets. You can treat these two as if they are insulating sheets. So what will be the field at the center? Because of the left, it will be this. Because of the right, it will be this. And both of them will give rise to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Okay, and what will be the sum?
0.
0. So that means electrostatic equilibrium is maintained. Okay, now let us take a point here and see. Because of the positive also, positive is always away from positive, therefore positive. This is also because of the other plate. Electric field because of the left plate, electric field because of the right plate. So sigma by 2 epsilon naught, sigma by 2 epsilon naught. What will be the sum? Got that?
Yes, ma'am.
Similarly, you can do for the other side also. So till now, so what did I say? They are going and sitting on the two surfaces and become sheets. So you can treat them as if they are insulators. Insulating sheets, and then look at their effect. Now, let us forget this isolated. Let us forget this isolated and think about conductors which are not isolated. Conductors which are charged and not isolated need not necessarily mean that they are in contact with each other. If they are in the vicinity or field of another charged conductor, then you say it is not isolated. If a charged conductor is not having any other conductor or field around it, then you say it is isolated. But if I have a conductor and I have another conductor also, and both are charged, then you can't call them isolated anymore. Each is experiencing the field of the other. You can't call them isolated anymore. So then what will happen? Let us see. I have one sheet. The thickness I have to show, it's a metal. I have another identical sheet. One carries plus Q charge, the other carries minus 2Q, minus Q charge. Okay? Now let us see how this is going to be different from isolated condition. Here what is going to happen is, in electrostatic equilibrium, charge will not go and occupy both surfaces of the sheet. Charge will not go and occupy both surfaces of the sheet. Because of attraction by this negative sheet, all the excess charge will go and sit on the inner surface. Similarly, here also, all the negative charges will go and sit on this inner surface. And they behave like two insulating sheets, positive sheet, negative sheet. Are you able to see that, guys?
Yes, ma'am.
Okay. Now, again, you want to find out what is going to be. So you can now treat them as if they are insulating sheets. You want to find out the field anywhere here, you can find out sigma by 2 epsilon naught and sigma by 2 epsilon naught. You add up, you'll get sigma by epsilon naught. Do you remember we got this answer in insulator when you had two sheets carrying equal and opposite charges? So you're getting the same result. Okay. And similarly, it can be shown that electric field is 0 here, electric field is 0 here. Inside the body, it is still 0. That is because here what happens is this negative fellow and the positive fellow, both their fields will oppose each other and give you 0. Similarly here also. So even now electrostatic equilibrium is achieved. So the crux of the matter is the charge is not adamant. The charge is just going to do its job to ensure that the electric field is 0 inside a metallic object, if it has to be in electrostatic equilibrium. To achieve that, it will do what is required. Is that fine?
Yes, ma'am.
That's it. Okay. So with this, I'm winding up the chapter. I just worked out the problem. You can just see this. Here also I worked out one. Then there is a third one I worked out. So in the current circumstances, I can't do better than this. See, for the last 4 days, I am on my bed only. So I didn't feel sick so much. I strained myself talking to you. I started feeling sick. Okay, so let's hope that I will be able to, whether it is a normal viral fever or COVID, whatever it is, I should be able to come back soon and handle the next chapter. This is almost the equivalent of 2 classes I have taken today. Any doubts?
All the previous surfaces, whether they are circles or line charge or sphere, all of those are insulators, ma'am.
Which one?
Previous surfaces that we discussed about.
Yeah.
First, all of them are insulators, ma'am.
All of them are?
Insulators.
No, from here. From here, we are talking of conductors. In insulators, electrostatic equilibrium will happen by itself. No charge will move. That is still yesterday.
Okay, ma'am.
Okay, now from this, this is not there for tomorrow's test. From what I have done today is not there for tomorrow's test. In conductors, on the other hand, charges will move. So they will move in such a way that electrostatic equilibrium is achieved. So how they move is what we have shown here. And for electrostatic, it's also necessary that the electric field outside has to be perpendicular to the surface, 0 inside. That's it. Have I cleared your doubt?
Yes, ma'am.
Okay. Any other doubts?
No, ma'am.
Okay. In that case, I'm just tomorrow. Please write the test. Don't miss. Don't expect us to give you makeup. Yeah, please don't do that because it's a lot of effort putting together so many questions for the sake of few students. Okay, then. Good day. All the best.
Thank you.
Yeah.